Alrighty, now we're on to section 3.5, and we want to define rank and nullity of a matrix. Okay, so this is their definition 3.5.1, and we're going to let A, try that again, not good with my letters, I guess, A be m by n, so m rows, n columns, then the column rank, so A, column rank of A, oh, they just use rank A, okay, so let me do that. They say that column rank A is, that's the dimension of the column space of A. Okay, so how many linearly independent columns does it have? And then the row rank of A is equal to the dimension of the row space of A. So how many independent rows does it have? And then the nullity of A is the dimension of the null space of A. Okay, so there are the definitions, and then they have this theorem 3.5.1, and so we've got the same matrix, so we let A be m by n, then we have a couple of things. One is that the column rank of A is equal to the row rank of A. So actually all we really need to talk about is the rank of A, okay, because they're the same. And then B, the column rank of A plus the nullity of A will sum to the number of columns n. So again, that's the number of columns there. And so that's really nice. And so then they go through and they mention, how do you find a basis? So find a basis for the row space of A. And essentially the procedure is use, the basis, use the non-zero rows of the reduced row echelon form of A. Okay, so just to show how this works, an example, if we let A equal, I gotta look back here to see what I used, 1, -1, 3, 2, 3, -2, and 3, 2, 1. If I have that matrix and I go find its reduced row echelon form of A, I get the matrix 1, 0, and 7/5, 0, 1, and -8/5, and 0, 0, 0. So what this tells me is I have these two non-zero rows. So that tells me right away the rank of A is equal to 2. And then the row space of A is equal to the span of 1, 0, and 7/5. Now, of course, I'm writing these two row vectors as column vectors, and 0, 1, -8/5. Now, and you can see, it's pretty easy to see when we take these vectors this way, that they are independent, because each non-zero row will have this leading column here, 1, 0, 0, and then 0, 1, 0. So there's no way to add the two rows together to get 0 other than to use coefficients of 0, right? Because there's no way to zero out. So let's make that less messy again. There's no way to zero out, that 1 except by multiplying it by 0, because everything else above it and below it are zeros, and same thing with the first one. And so this, is definitely a linearly independent set, but we know the row space of this matrix, B, I guess, if this is B, the row space of B is equal to the row space of A. And we had our theorem, I don't remember what number theorem that is, but we had our theorem that says that the row equivalent matrices have the same row spaces. And so, this set spans the same thing that the the rows of A span, these three rows. But this is definitely a linearly independent set that spans the space, and so it's a basis. Okay? And then that also tells us that the rank of A is 2. Okay, so that's finding a basis for the the row space. Try to not get my columns and rows mixed up here. Okay, now then, what about the finding a basis for the column space of A? Well, it's a similar sort of thing. What we want to do is we want to use the leading columns of, now this is where it's a little bit different. We want to use the leading columns of the reduced row echelon form of A to choose the columns of A for the column space. Okay, so our reduced row echelon form, let's write them both down here again. So A was equal to 1, -1, 3, 2, 3, -2, and 3, 2, 1. Okay, and B equal the, well, reduced row echelon form of A. And that was a 1, 0, and what was that? 5/8, 8/5, 7/5. That was 7/5. And then 0, 1, negative 8/5. And 0, 0, 0, like that. And so we take those leading columns there, and so there is our basis. Okay, so our basis is 1, 2, 3, and negative 1, 3, 2. Those first two columns of A. Okay, and that is basis is that for the column space of A. Okay, and again, you know, what do I want to say? I'm blanking out on what I want to say. Sorry about that. Oh, well, yeah, what I want to say was, so again, we see two vectors. The rank of A is 2, right? And it didn't matter whether we used the column space or the row space. It's in both cases based on the leading columns, right? Because in the row space, each leading column makes a new row. Okay, 1 row, 2 rows. But then, well, it's each leading column, so however many there are, and there are 2 of those. So, you know, every row has a leading column, and every leading column has a row associated with it, and where the 1 is, and so the rank ends up being the same. The rank is 2. And another way to kind of see that these two vectors should make the basis is think of the left to right idea. Okay, again, so I know I can make a basis out of the 3 vectors 1, 2, 3, negative 1, 3, 2, and 3, negative 2, 1. I know I can make a basis out of that for the column space. And so I start at the left, and notice that if I just stopped here, I would get that leading column. Oh, yeah, because it's independent. So then, if I go to this next spot, I would get the next leading column, showing that those 2 columns are independent. But then, when I go to this third column, notice it zeroes out down here, and these 2 values show me the non-trivial solution to write this third column in terms of the first 2. And so it's not independent, so I wouldn't want it. Okay, so really, you know, using this method to get a basis, we're just following the left to right rule, that constructive proof that we did, back in 3.3, I think? Could have been 3.4, 3.4, I guess. So we're just following that proof. And so these leading columns do tell us which of the columns of A are independent of each other. And so that's how we make our basis there. And thus we have a basis for our row space, a basis for our column space if we want it. And then, okay, how about a basis, you know, finding a basis for the null space of A. Whoops, for the null space of A. Okay. And now, so what we want to do here is we want to work with the columns that are not leading columns, right? And so, once again, let me write down that reduced row echelon form of A. Whoops. Okay, reduced row echelon form of A. And let's see, what do we have? We had 1, 0, and 7/5, and 0, 1, and negative 8/5, and 0, 0, 0. And so remember, again, that, yeah, these if I'm looking at a solution here for the null space of A, right? You know, I'm taking AX equals 0, and you know, so when I solve that, well, I could make a this leads to this augmented matrix 7/5, 0, and 0, 1, negative 8/5, 0, 0, 0, 0. So that's what it leads to. And so what that would say is that I can write, you know, x1 plus 7/5 x3 equals 0, and x2 minus 8/5 x3 equals 0. Okay, and so then I could write that as in a vector form. I could write x1, x2, x3. So there's any vector in my null space that I'm trying to get to is equal to, well, move, you know, this to the right hand side, and I get negative 7/5. I get an 8/5, making that positive. And what I'm going to do is, you see, I've got kind of this dummy variable here. I'm going to put a 1 for the x3. And notice that whatever I let x3 be, you know, say I let x3 be t, then this t times 1 gives me x3. This t times 8/5 gives me x2. And t times negative 7/5 gives me x1. Okay, so if that was maybe a little too fast for us, we'll take a moment here. We'll write this as negative 7/5 x3, and x2 as 8/5 x3. Right, so you tell me what x3 is. Well, okay, well, x3, we're going to call that t. Okay, but wait a minute. If x3 is t, I can substitute here and here. So I get x1, x2, x3. x1 equals minus 7/5 t. x2 equals 8/5 t. And x3 equals t. But now write that as t times, you know, a vector. Well, I shouldn't do the equals that way. So x1, x2, x3 as a vector then equals t times negative 7/5, 8/5, and 1. Okay, so you see what we were able to do is we're able to just take the given vector that the given vector that we got from our reduced row echelon form and fix it up that way. Use those values. We use the negatives of them, and then we need to toss in a 1 for each column. Okay, so let's do that with a couple extra columns. Okay, so suppose I started with a 2 by 5 matrix, and my reduced row echelon form of some matrix A ended up being something like 1, 0. Well, actually, let's not make that 0. Let's make that -2, then 0, then 3 and 4, and then here a 0. And a 0 needs to be a 0 because we need a leading column here, and then who knows, maybe this is a 0 as well, and that's a 5. Okay, so these columns correspond to an x1, an x2, x3, x4, x5 for an unknown. And so again, if I just take my time to, well, I can make that bigger, I guess. If I take my time to write out what this means, this says I have x1 minus 2x2, no x3, then plus 3x4, and plus 4x5 is equal to 0. And I have x3 plus 5x5 is equal to 0. Now, if I go with the x1 and the x3, so I've got x1. Now I'll need an x2. Well, so let me leave space for it. x3, we'll put an x2 in there, and an x4 and an x5. So if I solve for x1, I get 2x2, so the or the negative of -2, so +2, minus 3x4 and plus 4x5. And then x3 is just a minus 5x5. Okay, now x2, x4, and x5 are arbitrary. So let me call x2 R, let me call x4 S, and let me call x5 T, and make those substitutions, and I get an x1, x2, x3, x4, x5 is equal to, well, we've got the R and the X, the 2R there and R. So I'm going to write this as 2R, R, but then there are no other R's, so 0, 0, 0. And then plus X4 now, and X4 we have minus 3S, okay, because I substituted that. Nothing here, nothing there. So 0, 0, and then we have an S, and then we have a 0. And then plus, finally our T, so that's 4T, nothing there, negative 5T, and then nothing there, and then T, because that's what x5 is. So this I can write as the linear combination of R 2, 1, 0, 0, 0 plus S times negative 3, 0, 0, 1, 0, and then plus T times 4, 0, negative 5, 0, and 1. So you see what happened was the 2 and then the negative 3 and then the 4 and the negative 5, you know, you can read where I got those. There's the negative of negative 2 is positive 2. Then I had a negative 3, and then I had, oh, did I miss a negative on that 4 down here somewhere? Yes, I did. So sorry about that, just in case you were wondering how that became a negative, positive 4. It wasn't. That should be negative. Okay, so we had then the negative 4 and the negative 5 from that. So I just placed those in these vectors, but then I had to keep my spots for the columns here that that go with variables, so x2, x4, x5, that weren't leading columns. Okay, so and if you get something like this where you've got something inserted inside the leading columns, in between some leading columns, it just makes life a little more difficult, but it's not terrible. My suggestion is you go through and you take your time to write down things as I did, and substitute your variables and so forth. Just take your time the first few times through it to get this basis for your null space. But here we go. There is my basis for the null space. So null space of A is generated by the vectors 2, 1, 0, 0, 0. I don't know what A was, but if I had this reduced row echelon form, then I'm in great shape to generate the basis and write down the null space this way. Okay, so there's the null space of A. And again, in this case, I might have skipped past that, but notice here the dimension of the null space of A, okay, or the nullity, is equal to 3. And we had that according to this right here, the rank was 2, or the fact that we could go with the row space. But we had the rank of A was 2. So that's 2, and then when we take those 3 plus 2, we got 5, which was equal to our n, or number of columns. Okay, and if we go back up here, like I say, I think I jumped over that. Right here we have our nullity, or dimension of the null space, is 1, and our rank was 2. And so if we take the 2 plus 1, we got 3, which was equal to our n, number of columns in A. So that is this idea of the rank and nullity of a matrix, and finding bases for column space and row space and null space. So there's a lot there, and what you want to do is just kind of practice with this sort of thing, finding those spaces.